So, curve sketching for 3-6. This is basically a culmination of everything in Chapter 3. This is using the first derivative test. This is using the second derivative test. This is taking the intervals and checking concavity, checking for things being max and min points throughout. All right, so this is just everything all in one. So guidelines for analyzing the graph of a function. What we want to do first, we want to determine the domain and range of the function, determine the intercepts, asymptotes, and symmetry of the graph. We're going to locate the x values for which f prime of x and f double prime of x either are 0 or do not exist. You will use the rules to determine relative extrema and points of inflection. All right, so there's a lot going on here. All right, so here we go. We got the first one. We're going to do two problems. I'm not going to spend a lot of time going through how I got the derivatives. We did a lot of time. We did that a lot, right? We can talk through what they have and what they're used for. All right, so first off, we're going to take this guy. We're going to do everything we can with it. So f prime of x, my first derivative, it's going to end up being 20 over x squared minus 4 20 squared. Okay, that's what you get after you would do u substitution and so on and so forth, and then simplify. And then if I differentiate that, I'm going to get f double prime. F double prime of x is going to be negative 20, 3x squared plus 4. We'll use the quotient rule on this one, over x squared minus 4 quantity cubed. Low to high minus high to low over the square of what's below. And then I just simplified one. Okay. Now, from there, let's look at our x-intercepts. X-intercepts, take the original one, set it equal to 0, and solve, right? So the first one we would have, you would break down, you simplify x squared minus 9. You'd have, what, 2? On top, you'd have difference of two squares. So this will be x plus 3, x minus 3 on top, correct? And that would be 2 there. Divide both sides by x set it equal to 0. Divide both by x squared minus 4. Set them both equal to 0. So you end up, anyhow, after you would do all that, you end up with the points 3, 0, negative 3, 0, and 3, 0. That's your x-intercepts. And all I did was take the original equation, set it equal to 0, and solved. Huh? Very top one, yep. Okay, next thing, I need a y-intercept. Y-intercept, take the top one, plug a 0 in. Because anytime you have your y-intercept, your x value is going to be 0. So plug in a 0, I'm going to have 0 squared minus 9, be negative 9. On top is going to be negative 18. On the bottom is going to be negative 4. So negative 9 over 18, sorry, negative 18 over 4 would be 9 halves. Okay, that's my y-intercept. I just plugged a 0 into the original. All right, vertical asymptotes. Vertical asymptotes, we have to look at this thing and see what values are going to make this illegal. Okay, so looking at the top thing, the bottom would be x minus 2, x plus 2. It's a difference of two squares, right? So what two values will make that 0 on the bottom, making this an illegal function? 2 and negative 2. Okay? So vertical asymptotes are going to be at x equals negative 2 and x equals 2. All right, we're getting there. We are getting there. Horizontal asymptotes. Horizontal asymptotes, you would take the coefficients of what's given. What's the coefficient up top? It's 2, right? So I have a horizontal asymptote at y equals 2. All right. line the graph can't touch. It's like an invisible wall that's a barrier. Okay? So now we have to look at our critical points, our critical numbers. Remember when we found critical numbers? What to do is by looking at the derivatives, set them equal to 0. Okay, we're going to have a critical point at x equals 0. Okay, run through second derivative test. We have no inflection points. Okay, the domain, just check the domain to be all real, except for the two numbers we can't have. X cannot be plus or minus 2. And then we just need to take care of our test intervals. So our test intervals, we're going to be broken up by 2 and zeros, right? Asymptotes, critical numbers, those are where we break up the intervals. So we're going to look at negative infinity to negative 2, negative 2 to 0, 0 to 2, 2 to infinity. All right, and that just came from here and here. Okay, those are my critical points. Now, remember when we did those charts to check the inflection and concavity and all that good stuff? Remember those? All right, let's do that. That's lots of fun. I'm going to do a big chart here. Do my interval to be the sign or the value when I put in the original function. Then when I put it in the first derivative. When I put it in the second derivative. And then the characteristics. Oh, shnikes. I don't like that line. Can't draw a straight line. Characteristics. This chart. All right, so we have our intervals we just talked about. X less than negative 2, x equals negative 2, negative 2 is less than x is less than 0, x equals 0, 0 is less than x is less than 2, x equals 2, and 2 is less than x is less than infinity. There's all the intervals and all the values that we're going to check out. All right, so I'm not worried about the intervals with the original function, okay? I'm only worried about the first derivative and the second derivative. So say I'd use the number negative 3. Put a negative 3 into f prime of x, I get a negative. F double prime, I get a negative. So because f prime of x is negative, that means it's decreasing on that interval. And because it's negative for f double prime, what's my concavity, up or down? Down. So it'll be decreasing concave down in that interval.
So the point you said 30 or negative 30, that just comes from the.
I just picked a point in that interval. Yep. Okay. All right, so then the next one is an exact value. That's one of my critical points or critical values. I can plug that in. Well, if I plug that into the original, that's undefined, right? It's undefined. If it's undefined for f of x, then it will be undefined the whole way through. And the reason is that's a vertical asymptote, which we already listed out. All right, let's pick another number for the next interval. We could use negative 1. So if I plug in a negative 1, I don't care about the original function. All I care about is f prime and f double prime. So if I plug in a negative 1, f prime of x is going to be negative. f double prime would be positive. Since f prime of x is negative, it's decreasing. Since f double prime is positive, it would be concave up. Okay. At x is 0, when I plug that value in, well, that's my y-intercept because I got 9 over 2. F prime of x would be 0. And f double prime will be positive. Because I have a critical value that is 0 at f prime of x and it's positive for f double prime, and the fact of right before that it's concave up, this would have to be a minimal. All right, from 0 to 2. Again, I don't care about the original function. I just care about the sign for f prime of x and f double prime. So we could use 1. If I plug a 1 into f prime of x, I'm going to get positive. If I plug it into f double prime, I'm going to get a positive. Therefore, I am increasing because of f single prime. F double prime is positive. Therefore, it's going to be concave up. X equals 2. This is the same as x is negative 2. Undefined, undefined, undefined. That's because it's a vertical asymptote. And lastly, I get from 2 to infinity. Plug in like a 3. I don't care about the original. I just care about f prime and double prime. This would be positive. This guy would actually be negative. So now I'm looking at an increasing function that is concave down. A lot of information there, isn't it? Just for one graph. All right, so let's go ahead and graph this guy now. So I'm going to have asymptotes at 2 and negative 2, or y-intercept at 0, right? All right. And I also know that that's a minimum there. Okay, so why is it not drawing? There. There. All right, so I got vertical asymptotes at 2 and negative 2. Okay. I actually have a horizontal asymptote at 2. So there's my asymptotes. All right. Now, all right, so looking back here at my original, from negative infinity to negative 2, it is decreasing and concave down. So the only way I can be decreasing over the entire thing is to be below it, and concave down would look like that. If I'm above that line, I can't increase over the entire thing, can I? Because then I'm going to hit that asymptote at some point. Okay? Now, next thing is there's something weird going on at 0. So from negative 2 to 0, it has to be decreasing and concave up. But at the same time, at x equals 0, I have to be at 9 over 2, which is slightly bigger than 2, right? So it would look like this. Boom. Kind of like parabola looking thing. Then the exact opposite would happen right after that. So right after 0, it's increasing and concave up. It would look like this. What's that? Yeah. So it'll be up here. Good call. I messed up the fraction in my head.
Because of that, I think you should accept on each page.
I like this on that.
Okay, here and here. All right, and then lastly, from 2 to infinity, we're increasing and also concave up. Or sorry, concave down. We could be back below. Looks like this. So that is what our graph would look like for f of x equals 2, x squared minus 9 over x squared minus 4. Question. What Desmos will be quite good.
What does concave mean?
It's whether it's facing up or down. This is concave down. Okay. This is concave up.
Okay.
Okay. Questions. Let's stop right there for today. We'll do one more tomorrow.